Yeah. So this is my project. I will start with the preface. So under the theory of general relativity, clocks further from a gravitational source run more quickly than clocks closer to the source. Additionally, under the theory of special relativity, clocks moving at high speeds run more slowly than stationary clocks. Both of these effects occur in simultaneously. This is all relative to the reference frame of a stationary person close to a gravitational source. So you might be thinking, whoa, general relativity, special relativity, what does this have to do with mechanics? Well, let me show you how I integrated this into my project. So here's my universal constants and problem scenario constants. So I have a couple problem statements throughout this, but let's start at this one. So I decided to figure out for an airplane moving vertically at a constant velocity v equals 0.01 c, at what distance from the center of the Earth does it need to be in order for gravitational time dilation to cancel out with the inertial time dilation, which we'll call, for the sake of this project, temporal equilibrium. This is like the special height that we'll also call the critical height, so it's interchangeable. But so basically, from a reference frame from our height, an airplane would be flying at a velocity that makes their time look slower. But also they would be further off the ground, further away from gravity, so it would also make their time go faster. So I kind of want to figure out what that point is where they would both cancel, the dilations would both cancel out. So here's just a simple example of finding this critical height, which I derived from this using this. So I basically did a time dilation due to both relativity effects. So basically setting them, the product of them equal to the time, the proper time, and the time of our reference frame. And so basically we want this to equal 1 so that our t prime and our t would be equal. So there would be no, so it would basically cancel out the dilations. So I set them equal to 1, and this is how we derived this equation for r, which would technically be our height in this case, because our plane is vertical, traveling vertically. So going back to this is how I got this equation. And so the critical height from the Earth center is 88.7 blah, blah, blah meters when traveling with a velocity of 0.01 c. So that's a pretty easy example. But now we want to find the relationship between velocity and the critical height starting at the Earth's surface. So here's my code for the Earth's, the velocities. As we change our velocities, how will that affect our height, our critical height for each velocity? And then I'm going to plot this on this graph here for critical height versus velocity. And as you can see, it has a inversely proportional relationship. So this makes sense because as an object moves faster, it sees everything around it moving slowly. In contrast, as an object gets closer to a gravitational source, it sees everything around it moving faster. Thus, the faster an object moves, the closer it needs to be to a gravitational source in order for the time dilation effects to cancel out. In particularly, velocity and critical height are approximately like inversely proportional, which is shown in this graph, as I just said. So let's move on to problem statement number 3. Now we want to know how much work is being done by linear and quadratic drag forces on an airplane traveling vertically from the ground at given velocities as it approaches the respective critical height, which we calculated in this problem statement 2. So we're going to take these critical heights and velocities that we used in this problem, and we're going to plug them in to the work with linear drag and the work done with quadratic drag. So here we have our linear drag coefficients of an airplane and our quadratic drag coefficients of an airplane, which this is how I calculated them using these formulas. And I made them negative for the sake of just plugging them into the equations. So then now we're going to plot out these relationships on a graph. So here are the graphs with work with linear drag versus velocity and work with quadratic drag versus velocity. And then as you can see from the graphs, quadratic drag has a significantly greater contribution to work than linear drag. This is because both the velocities and critical heights are significantly large enough that the quadratic drag dominates over the linear drag. As you can see with this, you can kind of see with these axis corrections in these corners here, how it has a greater how it has a greater effect on work. So now problem statement 4. We want to find the total work done by non-conservative forces on an airplane traveling vertically at constant acceleration A equals 554,000 meters per second squared. Starting from the ground at rest as it approaches a height where it achieves temporal equilibrium. We want both a numerical, adding up all the work done between small time steps, and an analytical solution using the line integral over vector field formulation, which I will show you after I show you the numerical calculation here. So here we have our initial conditions where we have a constant acceleration, velocity of 0, and our current height, which is initially the surface of the Earth from the core of the Earth. And then we have our time step to update S as being 0.00001. And we want to add up all the external work until reaching that temporal equilibrium, this height right here. So we're simulating our kinematic equations, and then here we're going to calculate the change in energy from the previous time step to the current time step. And then we're going to add it to the work, and then we're going to make it the current time step equal the previous time step. So it updates this while loop because we want it to continue working until it is greater than or it exceeds that critical point, because then we know it reached it, and then it'll spit out the velocity and the height at which the airplane, the vertical airplane, reaches this. So then the total work done by non-conservative forces is approximately this number right here. And so now I'll show you my analytic solution using the line integral over vector field formulation. Should be here, right here. Okay. All right. So I wrote it out. So the analytical solution for total work done by non-conservative forces. Yeah, did I say that this is non-conservative? Yeah, I did. Okay. So this is, I drew out my airplane taking off vertically, which is theoretically impossible. But for this example, it is taking off vertically. And so it would have your non-conservative forces going in this direction, your conservative forces, which is just equal to gravity, mg, going downwards. So the work would equal the force, the non-conservative forces dotted with the directional vector, and it would equal force of non-conservative times dy, since it's traveling in the vertical direction. Now we want the force conservative plus the force non-conservative, which will equal the net F net force from Newton's second law. We can set that equal to mass times acceleration. This force of non-conservative forces will equal MA minus FC, conservative forces, and then we can set this conservative force mg, plug that into MA minus mg, and we get MA minus mg. And then we can plug that in for our non-conservative forces vector times dy, or not vector magnitude times dy, and integrate this to get this equation, m times a minus g times height final, which should be equal to, approximately equal to, our numerical solution. Simplifying assumptions, booster mass are negligible, and acceleration is constant. So let's move down to this work right here. V equals V naught plus AT, which is just equal to AT, and height is equal to h naught plus 1/2 AT squared from our kinematic equations, which height is also our height. We also want it equal to the critical height formula. And so we can get our height by, our initial height, we want to be the radius of Earth. So then we can plug these, what we know, into this equation, set them equal to each other, and solve for t. So doing this, solving for t, we get this giant equation right here, but we finally get an answer, 0.02019145 seconds. So then we can finally plug in for our height final by using this formula right here. And then we can plug that in to get this as our height final, which matches up with our code. What? Yeah, this just matches up with our height right here, and our velocity also matches. So yeah, right here, because we can plug this back into v equals AT and get our velocity, and then we can solve for our work. And plug all those numbers into our work equations, and this is the answer I got, my analytical solution. So yeah, overall, this is my project using the concepts of mechanics, and I hope you enjoy. Thank you so much. I hope it recorded. Oh wait.